is Lesson 6, Inverse Relations and Functions. Our essential question is, how can you find the inverse of a function and verify the two functions are inverses? And here is our table of contents. Represent the inverse of a relation. What is the inverse of the relation represented in the table? So I have an inverse relation, so I can recall that a relation is any set of ordered pairs x, y, where x is the independent variable and y is the dependent variable. An inverse relation is formed when the roles of the independent and dependent variables are reversed. So basically, I change my x and my y, I just flip-flop them. So my original relation is a function. I flip them, so my x's become my y values and my y becomes my x values, okay? And I look at my values. I notice that I have two x's that equal 1, but their y values are different. This means that it's not a function, so it doesn't follow that one-to-one rule, which means that I have an x value of 1, but it's going to two different numbers, okay? So this one is not a function. Now, if this were 0, -2, then it would be a function. Okay. So all the x values have to be different and they have to go to a different y value. Okay. So if an inverse relation of a function f is itself a function, it is called the inverse function of f, which is written f to the -1 power of x. Find an equation of an inverse relation. Let f of x equals x squared. How can you represent the inverse relation of f algebraically? Okay. So again, all I'm doing when I'm talking about inverse functions is I'm flipping the x and y. So instead of y equals x squared, I'm going to have x equals y squared. And I'm going to solve for y value. Okay. So I have x equals y squared. So in order to undo that square, okay, the inverse operation of a square root, or of squaring is a square root. So I'm going to square root both sides. So I get y equals plus or minus the square root of x. Okay, the inverse of f can be represented algebraically by the equation y equals plus or minus the square root of x. How are the graphs of y equals x squared and y equals plus or minus the square root of x related? Okay, so this is what they look like. My pink is that y equals x squared, that original function, and the inverse of f, or plus or minus the square root of f. Okay, so basically all I did was over this green line, if I were to fold it in half along that y equals x line, they would create the exact same function. Okay. The graph of the inverse of f is the reflection of the graph of y equals x squared across the line y equals x. Restrict a domain to produce an inverse function. So consider again the function f of x equals x squared. Under what domain will the inverse relation also be a function? So if I'm looking at my original graph, so if I looked at that graph, right, if I draw any line, any vertical line up and down, it's going to cross at 2 points, which means it's not a function. Okay, so what I'm doing is I'm restricting the domain for my function to determine how it can create a relation. Okay, so the inverse relation is not a function since it could contain the inverse of both the points 4, -2 and 4, 2. Okay. So for the inverse of a function, all the duplicate y values would have to be eliminated from the original function. So I can restrict the domain of f to be x is less than or greater than or equal to 0. Okay. So when I do that and I graph it, if a function has two x values for the same y value, its inverse will not be a function. You can restrict the domain in many different ways to create a function that will have an inverse that is a function. So example, y equals f of x. So this whole y equals f of x, where f of x equals x squared. Okay, so that blue line would just continue like a normal parabola. But if I'm graphing it over the line y equals x and I still want it to be a function, I'm going to have the inverse of x, but I'm going to restrict that domain. Okay, so the inverse relation of f of x equals x squared is y equals plus or minus the square root of x. If the domain of f of x equals x squared is restricted to x is greater than or equal to 0, then the inverse is the function, defined as f to the negative 1 of x equals the square root of x. Okay. You could also do this as x is less than or equal to 0. Okay, then it would just be negative square root of x would be your function. Find an equation of an inverse function. Find an equation of the inverse function of f of x equals the square root of x minus 2. Okay. The graph shows that no horizontal line intersects the graph in more than one point when the graph is reflected over the line y equals x to produce an inverse. There will be no vertical line that will intersect the graph more than once. Since the inverse will pass the vertical line test, the inverse relation will be a function. So if I'm looking at this, right? So I've got y equals the square root of x minus 2. So that's what this function looks like. Okay. I'm flip-flopping the domains. So the domain of f is x is greater than 2. So the range of the inverse of f is y is greater than 2. The range of my original function is y is greater than 0. So the domain of my inverse function will be x is greater than 0. Okay. You can switch the roles for x and y and then solve for y. So y equals the square root of x minus 2 becomes x equals the square root of y minus 2. I square both sides to get rid of this square root. So I get x squared equals y minus 2, and then I add 2 to both sides. So my inverse function is y equals x squared plus 2. So the graphs of f and the inverse of f are both functions on our reflections over the line y equals x. Find an equation of the inverse function of f of x equals negative the cube root of 4x. The graph shows that no horizontal line intersects the graph in more than one point, so the inverse relation will be a function. So here's my original. So again, if I have a horizontal line, there's no point that's going to cross more than once. Okay. I can flip-flop my x and y values, and I can solve for y. So I get x equals negative the cube root of 4y. I need to cube both sides. So I get x cubed equals negative 4y, and then divide both sides by negative 4. So you can see here, my pink is my original. My blue is my inverse function. And this green line here, y equals x, is the line that I'm reflecting across. All right, since the inverse is a function, the inverse of f of x equals negative x cubed divided by 4. Use composition to verify inverse functions. What is the inverse of f of x equals 2x plus 5, and how can you verify this? Okay, so 2x plus 5 equals y. Remember that f of x is the same thing as y. And I'm just going to flip the x and the y. Okay, so that gives me 2y plus 5 equals x. Now I'm going to solve for y. Okay, so I subtract 5 from both sides. That gives me 2y equals x minus 5, and then I divide both sides by 2. So I get y equals x minus 5 divided by 2. Okay, so the inverse of f of x equals g of x equals 1/2 x minus 5 halves. You can also write it as g of x equals x minus 5 divided by 2. Either way will work. Okay. You can verify that they're inverses of each other by taking f of g of x and g of f of x to determine if they both equal x. So f of g of x, so f of 1/2 x minus 5 halves. Again, I'm substituting that value in for my x value. So I get 2 times 1/2 x minus 5 halves plus 5, which gives me x minus 5 plus 5, which gives me just x. And then g of f of x, so g of 2x plus 5. Again, I'm substituting in for x. I get 1/2 times the quantity 2x plus 5 minus 5 halves. So that gives me x plus 5 halves minus 5 halves. So that gives me just x. Since f of g of x and g of f of x both equal x, they're inverses of each other. Okay. You can also verify that they are inverses through graphing. Okay, by looking at this, you can see that they're reflected, the pink line's reflected over that y equals x line to create that green line. are the two functions f of x equals x squared plus 5 and g of x equals the square root of x minus 5 inverses of each other. Okay. Again, to be inverses, f of g of x and g of f of x must both be at the identity function, or y equals x. Okay. So I start with f of x equals x squared plus 5 and g of x equals the square root of x minus 5. Okay. And I substitute this in. So f of g of x is f of the square root of x minus 5. Square root of x minus 5 squared plus 5 gives me x squared minus 5 square root of x minus 5 square root of x plus 25, or equals x squared minus 10 square root of x plus 25. And then g of f of x is g of x squared plus 5. So the square root of x squared plus 5 minus 5 gives me the square root of x squared plus 5 minus 5. I can't simplify that any further. Neither of these are equal to the identity function, which means that these are not inverses of each other. Rewrite a formula. Okay, chocolate artist Amara Guichon recently created the Daily Planet statue entirely out of chocolate. To create the globe, he used a mold that could hold 4.5 liters of chocolate. What is the radius of the mold if he fills the mold entirely with chocolate? So the volume of a sphere is calculated using the formula V equals 4/3 pi r cubed. We can rewrite this formula so that we can solve it for the radius. I do that by dividing both sides by 4/3, okay, which is really the same thing as multiplying V times 3/4 equals pi r cubed. Okay, then I divided both sides by pi, and then I took the cube root of both sides. So my radius, to find the radius, of this function, I'm taking r equals the cube root of 3/4 v divided by pi. So now that I have that information, since a liter is a measure of capacity or volume, it can be expressed using cubic units of length. When you take the cube root of an expression involving volume in cubic units of length, the units of the result will be the correct units to describe the length. 1 liter is equivalent to 1,000 centimeters cubed. So 4.5 liters is equivalent to 4,500 centimeters cubed. Since I know this information, 4.5 liters, again, is 4,500 centimeters cubed, I can substitute that value in for volume and then solve this equation to find what my radius potentially could be. So I take the cube root of 3/4 times 4,500 centimeters cubed divided by pi equals r. So my radius, when I substitute this into a calculator, gives me approximately 10.2 centimeters. So rewriting the equation to show r in terms of v is similar to finding the inverse. In effect, you are exchanging the roles of the dependent and independent variables. So again, v equals 4/3 pi r cubed. In the original equation, you can see that v depends on the value of r. V is my dependent variable, r is my independent variable. Okay. In this form, when I'm solved for the radius, you can see how the value of r can be determined by and depends on a given value of v. Summary. Okay. So in conclusion, we talked about inverse relations. You can determine if it's an inverse relation by just simply switching the x and the y values. You also need to double check and make sure that both the original equation as well as the inverse relation are actually both functions. So if a value has the same x value and different y values, it's not one-to-one, so therefore it is not a function. I can exchange the roles of the independent and dependent variables and solve for the new dependent variable. In other words, I'm switching the x and the y values and then solving for the new y value. The graphs of f and the inverse of f are both functions and are reflections over the line y equals x. And you can see this for both of these graphs here. Again, I'm having the inverse of, I start with a function, I'm reflecting it over that line of y equals x. When I reflect the graph across the line y equals x, if necessary, you can restrict the domain of the original function to find an appropriate inverse for the function. So especially when you're dealing with x squared or x to the fourth values, you're going to probably have to restrict that domain just because of the fact that when you flip it over, it doesn't become a function. And that is the end of Unit 5, Lesson 6.